Hi, I'm Magnus Morton, and today I'll be talking about DelayRepay, delayed execution for Kernel Fusion in Python. I'll begin with the executive summary. Can we use delayed evaluation to improve the performance of numerical Python workflows on GPUs? The answer is yes. I'll just outline the rest of this talk for us. I'll begin by talking about the context of what we're doing. Then I'll describe the design and implementation of our system. I'll present some experimental results. And finally, I'll attempt to draw some conclusions and summarize. So on to the context. So starting with data science, though I'm really talking about scientific programming here. And really I'm focusing on programming with arrays. For this, high performance is critically important, particularly when large data sets are used. Though also often when small data sets are used, performance is very important. Though really, performance is very important for everything. Traditionally, programmers have used Fortran for this stuff, and many still do. R, Mathematica, and MATLAB became popular alternatives, particularly for statistics and engineering. Now, Python has become extremely popular for data science and machine learning. Python, and its CPython implementation particularly, is not a high-performance language and is pretty unapologetic about that. In spite of this, Python is extremely popular for data science. So we have a sort of contrast here before the very slow language and the very high performance domain that people are using it for. So how do we reconcile this? So data scientists and numerical programmers don't use Python directly. They use, or the Python interpreter so much, they use libraries such as NumPy, SciPy, TensorFlow, and so on, which are all implemented in native code, and often in Fortran, and that allows them to combine the user friendliness of familiarity and easy use of Python with these high performance libraries. The dynamic nature of Python also supports iterative and rapid development, as evinced through popular tools like the Jupyter notebooks and so on. And that's another reason you see this use of Python in this domain as well. So we're now in the age of heterogeneous accelerators. So Moore's law is no longer manifesting in improved CPU performance year on year. That improved performance, to get the benefit of the transistor density these days, you have to use some fancy hardware. So I'm talking GPUs, field programmable gate arrays, coarse-grained refigurable accelerators, ASICs, that sort of thing. And hardware like this can give extremely good speedups versus CPU code alone, particularly when we're talking about array-based programs that we see in data science and machine learning. However, they can be very painful to program, often requiring a programming model radically different from that from a CPU. This, of course, means that existing code has to be rewritten. This can be particularly bad for data scientists who may have little experience in writing low-level code to start with, or managing device interaction, and may be blissfully unaware there are such things as other programming models. And even for people who are programmers at low level, having to turning their code almost inside out to take advantage of a GPU can be quite tricky. So for this talk and this work we've been looking at, we're particularly concerned about making this easy by using GPUs through Python. And many people have attempted to solve this problem. There are many GPU tools and libraries for Python, particularly NumPy, PyCUDA, PyOpenCL, and CuPy. They're some of the most well-known ones. So NumPy is quite a popular tool for NumPy for not just for running on GPUs, but for compiling NumPy and Python code to just in time to native execution. But it does allow you to schedule your code on a GPU as well. PyCUDA and PyOpenCL are more traditional wrapper libraries around the low-level CUDA and OpenCL APIs, and they don't really provide a new way of writing the kernels themselves. And then we have QPy, which is a drop-in replacement for NumPy for running NumPy operations through CUDA. Our work builds on QPy, and we'll be directly comparing our approach and performance to QPy. Many of these libraries require rewriting existing NumPy code, or they require knowledge of GPU architecture such as workgroup size and so on. So to use Numba, for example, you would have to, it's not as simple as just, you have to rewrite part of your NumPy functions to take advantage of the GPU thing. And you have to use Numba in the first place, which requires, it's not a case of just changing an import, for example, in your NumPy code, whereas using QPy allows you to just change an import and you have immediate GPU acceleration. But drop-in libraries such as QPy also leave performance on the table. And part of the reason for this, of these libraries having less performance as they could have, is that they do not have support for kernel fusion, for automatic kernel fusion. Kernel fusion is where multiple GPU kernels are combined into a single kernel. This can give significant performance improvements via locality improvements, reduced loads and stores, and simply less time spent compiling the kernels. This is particularly important when we're doing development iteratively or interactively in Python, where these sort of kernel compilations can start to really affect your latency and so on. As a motivating example, here's a simple NumPy-like program that will sim as running on a GPU. Though a very smart system will be able to tell this doesn't need to be accelerated at all, as the answer is always 1, but never mind. So without fusion, we need 5 kernel calls. So as per the example, we have 1 kernel call per arithmetic operator and arithmetic function. If we used kernel fusion, we would only need 1 kernel call. And we could hopefully get at least a 4 times speedup on that computation by fusing these kernels together. So our solution to the performance gap is DelayRepay. So DelayRepay is a drop-in replacement for NumPy, which improves performance over existing solutions for free using delayed evaluation and kernel fusion. Now we move on to the design and implementation of DelayRepay. We want to gain the benefit of kernel fusion without changing any existing code or minimizing it as much as possible. This is our key goal with this work. We want to replicate the NumPy API exactly and fall back when not supported, as it was not perhaps feasible to re-implement every single NumPy function on a GPU, but we want to maintain we still want everything that even though we don't support to still work, so graceful fallback is implemented. The only change DelayRepay requires to existing code is import statements. Here's an existing NumPy program. It's a very simple one. And here's the equivalent DelayRepay program on the right here. The only change is the import NumPy on the left is now import DelayRepay. That's the only change we require to use our system. We thought that delayed evaluation may be a good way to achieve kernel fusion. By delayed evaluation, we mean that we will not evaluate parts of the program until they are needed. We are only delaying the NumPy part of the program. Any other Python gets eagerly evaluated. Doing this allows us to combine the NumPy operations at a high level and to easily generate fused kernels. This avoids the need to fuse distinct CUDA kernels together. To achieve this, we need to generate a delayed execution graph of NumPy operations. We overload the NumPy array types and operations to return DelayRepay nodes. And we essentially generate something at the implementation level, at least, that is very much like an abstract syntax tree of NumPy operations. And to do this, we heavily leverage Python's object ability to subclass and change types at runtime or change function definitions, and as well as we mess with the import system greatly. So here's a previous Pythagorean identity example, again, showing how that each step of the computation we return a DelayRepay type rather than returning the eager result, and how each step builds on the previous step of the computation. So we can see how we basically build up a tree of delayed computations as Python objects. And we can see this clearly when we look at the tree representation of the same computation. We can see how the higher level nodes compose the others. Note that in this example, both NP array data are they're not distinct nodes, they are the same nodes. And our runtime system is aware of this and leverages this to improve, to memorize performance, memorize results, or memorize these trees as they're computed. In order for this to be useful, we need to eventually evaluate a delayed graph. Evaluation is forced when a DelayRepay type leaves the DelayRepay context. Here's a non-exhaustive list of when this can happen. A print function, unsupported NumPy function, conversion to a list, getting a string representation, a non-NumPy function or method, or a comparison function. This is a non-exhaustive list but covers nearly all the cases we've seen. Evaluation, of course, triggers CUDA kernel generation, compilation, and execution. Evaluation will return a NumPy array wrapped in DelayRepay type, allowing the cycle to begin again. We use QPy to generate CUDA kernels, and QPy also manages device memory, data transfer, and scheduling. This saves a lot of boilerplate coding. The code is generated by walking our delayed execution graph and generating static single assignment expressions in CUDA. These SSA expressions are spliced into a QPy kernel template. We use aggressive caching and memorization to avoid revisiting nodes and to reuse existing fragments. This is self-contained within a run and is separate from standard CUDA kernel caching, which we will use if available. We also do common subexpression elimination and something I'll call scalar partial evaluation. Because this is done dynamically just in time, we can treat scalar variables as constants and fold them into the generated kernels directly, as well as possible performance boost. This avoids the need to transfer variables and avoids hacks like wrapping them in single element arrays, which is relatively common in the GPU world. Some have asked, why do this in Python and not just apply this technique to a more performant language like C++ or Fortran or something? One reason is Python's popularity. Python is popular for data science and scientific programming, and there's a rich ecosystem that might benefit from this. Another reason, and my personal reason for this, is that Python's object model and support for patching existing types and functions make this work much easier than it would have been in any language more rigid or lower level than Python. So I would suspect this to take at least 3 times or more longer to do this in C++ than in Python. So now we move on to the evaluation of the delayed evaluation system. We benchmark DelayRepay against CuPy, Borium, and NumPy. Borium is a GPU library for Python which claims some support for Kernel Fusion. We use a suite of NumPy macro-ish benchmarks as far as possible, all run on the server with an NVIDIA Tesla K20. We measured the computational kernel time, meaning the time spent on device alone as tightly as possible. And we also measure the end-to-end or cold time, which includes everything such as warm-up, virtual machine startup, and so on, with all kernel caches dropped. I think this bit is particularly useful to look at as users interact with Python programs well, interactively, and will be modifying things as they develop iteratively. So, I mean, a very tight, very performant kernel is not much use if it takes 3 times as long to start it and transfer the data in the first place. So let's take a look at the computational kernels, or warm times. In this chart, blue is CuPy, orange is Borium, and green is DelayRepay. Each bar represents the speedup relative to NumPy, and this is a logarithmic plot. We can see that we almost always see a speedup for all of the libraries, except for a few slowdowns for Borium. We can see that DelayRepay almost always produces the best speedup. Using the geometric mean, Borium has an average speedup of over NumPy of 11, CuPy 15, and DelayRepay 24. Over all the benchmarks, Borium has a maximum speedup of 203, CuPy 74, and DelayRepay 377. For the cold or end-to-end results, as we discussed previously, we see quite a different picture. CuPy and Borium generally produce a slowdown compared to NumPy. So this is an example of perhaps using a one-size-fits-all or Dropin GPU solution maybe doesn't produce the performance you wanted. So, but our Dropin solution, DelayRepay, produces a speedup on the geometric average. So taking a closer look, again using the geometric mean, Borium has an average speedup over NumPy of, well, not speedup at all really, of 0.37, CuPy 0.77, and DelayRepay 1.25. So that's a 25% speedup. In terms of the maxima, Borium has a maximum speedup of 3.85, CuPy 3.75, and DelayRepay 6.79. This chart shows the memory usage of Borium and DelayRepay compared to CuPy. In most cases, we can see a reduction in memory usage. There are 2 cases here. Borium has a memory usage of 0, but that's a result of a failure in instrumentation. We have one example here where DelayRepay is significantly worse than Borium, but we'll talk about that one in just a moment. So we generally see a significant speedup for DelayRepay over CuPy, Borium, and NumPy, along with reduced device memory usage. We have one case where DelayRepay makes things significantly worse. This is the case of the hand-coded neural network benchmark here. So DelayRepay is significantly worse in both memory consumption and execution time end-to-end. So this program has many random constants in it, and our constant folding engine folds each and every one of those random constants as a constant in each in the NumPy kernel. This means that we are now unable to cache these kernels, and a new kernel is generated for each input, resulting in the terrible slowdown. So it should be fairly straightforward to fix that in the future. Okay, so in future work we have several ideas for future directions. We're looking at creating a lift backend for DelayRepay. Lift is a functional intermediate representation and code generation framework. This will enable us to target other devices such as coarse-grained reconfigurable accelerators and allows further optimizations. Though, yeah, we're now looking at lift and lift, possibly a successor to lift as well. We would like to add a heuristic or machine learning based decision system to the runtime. This would allow us to fall back to NumPy when running on GPU would be worse than on CPU. And there's a couple of occasions in our results where that is the case. We will obviously be adding support for further NumPy and SciPy kernels. So if there's a few matrix operations here and there we don't support, which we'd like to, that sort of thing. Finally, we'd like to investigate how this technique could help improve performance on CPU only. So it's not obvious if it's going to work yet or not, but it seems like there might be a possibility if we do this just on NumPy expressions themselves, by fusing them together, that we would get some benefit of cache locality on CPU as well. How much this would be and whether it would offset the small overhead in doing so is yet to be seen, whether it's worthwhile doing or not, but we're actively investigating this. So in summary, with DelayRepay, we use delayed evaluation to enable kernel fusion on GPUs in Python. We have shown significant performance improvements without modifying existing code beyond changing some imports in Python programming. Thanks for listening to my talk. I hope I've inspired you all to read the full paper, which was published at the Dynamic Language Symposium 2020, and I will answer any questions you might have. Thank you.